All right, let's start. Hello, everyone. Today is the first TCS Plus talk of 2017, and the operator of it will be Aded Regev from NYU. Right now, he will go around the table and introduce the groups that join us today.
Hi, okay, and welcome, Ilya. Thanks for being the moderator. Let me quickly go around the table, see everyone is here. So we have Anindya Day, also one of the people here behind the operation. Hi, Anindya. We have Dimitris Paparas from University of Wisconsin-Madison in the group. Hi, guys. We have Jiapeng Zhang from UCSD and here. Hi, guys from UCSD. Hi. We have K. Gopalakrishnan from East Carolina. Hello, welcome again. We have Syed Hassan joining from, you have to help me there, from UC, right, I knew that. Welcome. We have Shravas Rao with the group from NYU. Hi, Shravas. A few floors above me. We have Sina Shehan from University of Michigan. Hello, everyone. We have Sorachai joining us from Michigan State University. Hello, good to see you again. And we have Srinivasan from CWI. Hello, guys. And we have the group from Caltech. Thomas Vidic with the group from Caltech. Okay, so back to you, Ilya.
Thanks, Aded. Before we will start today's talk, let me say a couple of words about the upcoming ones. First of all, in 2 weeks, Jelani Nelson from Harvard will talk about optimality of Johnson-Lindenstrauss lemma for dimension reduction in Euclidean space. And then, in 4 weeks from now, Josh Allman from MIT will talk about rigidity, or rather non-rigidity of Hadamard matrices. Okay, let's finally start today's talk. First of all, it would be really great if the audience would ask questions. And for this, before you want to ask a question, you need to unmute the mic by pressing a button. As for today's speaker, we are very happy to have Nikhil Bansal from Technical University of Eindhoven. Nikhil has done lots of exciting work, mostly on approximation and online algorithms and optimization. And in particular, most relevant to today's talk is his breakthrough paper from Fox 2010, where Nikhil made a classic result of Spencer from 80s on discrepancy algorithmic. This work triggered a lot of other beautiful papers, and today's talk will be on one of them. And the talk is called Discrepancy Beyond Partial Coloring. Welcome, Nikhil.
Okay, thank you. Can you hear me well?
Yes.
Okay.
Good. You, for some reason, I still can't see you, but is it okay on your side, Ilya?
Can you see me?
Now it's okay, yeah. So go ahead. Hopefully it's fine.
Okay. So, yeah. This is based on recent joint works with Daniel Dadouche and Shashwat Garg, who's a PhD student here. So we all know what
I'm sorry, there's a problem. We can't see the slides. I think we're not the only ones. With that, I don't know.
Yeah, here it's okay now. There was for a second I lost it.
See him.
Yeah, we've had it before. Sometimes takes a couple of seconds to stabilize. Let me try something here. Okay. Can you see him now?
This works for us now.
Okay, so I'll keep it that way. Okay, if there's trouble, let me know.
Yeah, I can see it too now. Yeah. Okay. Okay, so good. So discrepancy problem is the following. So you're given a universe of elements 1 through n and some sets S1 through Sm. And you want to color your elements red and blue so that each set is colored as evenly as possible. Right? So mathematically, you can think of coloring your elements +1 and -1. And then what you care about is you look at a particular set S, and if you sum up all the colors, right? So this sort of absolute difference will measure the imbalance between reds and blues, or plus and minuses. And you take maximum over all the sets, and that's the discrepancy of your particular coloring. And the goal is to find a minimum discrepancy coloring. So that's the discrepancy problem for a given set system. Now, in general, there is nothing special about a set system. In general, one can think of a matrix. So a set system would just correspond to like the incidence matrix, where column correspond to the elements and rows correspond to the sets. And now you can ask the problem that given any matrix A, you want to find a coloring, right? So you want to color or multiply the columns by +1 and -1, and you care to minimize the L infinity norm of this product, right? So it's easy to see it's the same if A is the incidence matrix of a set system. And again, so that would be the discrepancy of this matrix. So most work in discrepancy sort of started with combinatorics. So people mostly talk about set systems, but almost all techniques sort of generalize to matrices. So I'll kind of go back and forth between these two notations. Good. So the notion of discrepancy comes up in many different areas, sometimes quite surprising. So in CS, it has been very popular for a long time. In mathematics, it also comes up quite naturally. And there are sort of many classic books on this topic by now. So we won't sort of discuss why in this talk why it comes up so frequently, but yeah, sort of a basic notion. Okay. So to get a feel for what kind of questions people look at, let's look at sort of 3 classic examples in the area. So the first example is what's called the Tusnady's problem in 2 dimensions. So here you are given n points, which are placed arbitrarily in some grid. And what you want to do is you want to color these points red and blue, so that you want to minimize the discrepancy with respect to axis parallel rectangles. So I'll color these points somehow red and blue, and then if I look at any axis parallel rectangle, like here with these dotted lines, so you sort of look at its discrepancy, and then you define the discrepancy of this coloring as the maximum over all such rectangles. Right? So that would be a discrepancy. Now, one thing to notice is if you did a random coloring of these points, you should expect at least about a root n discrepancy, right? Because even if this points were on a line, you would expect like the first half to get maybe n over, like a root n bias compared to the other half. Right? So yeah, so it's not hard to see that random sort of, you always lose root n. And what's very surprising is for this particular example, for example, it's easy to get polylogs, so substantially better than what random would give you. And for this problem, there has been a very long line of work. In fact, for a long time, the best known was log to the 2.5n due to Banaszczyk. And only very recently, it has been improved all the way to log 1.5. So in fact, this Nikolov's result is less than 2 weeks old now. So, and we'll see sort of some of this in this talk. A second sort of classic problem is what's called Steinitz problem. So here you are given vectors in d dimensions with L infinity norm 1. So the entries are between -1 and 1. And you want to minimize the discrepancy of prefix sums. Right? So you want to find some coloring x, which is +1 -1, so that if you look at the signed sum of any prefix, like in any coordinate, you want to bound how big it can be. Right? So this would be the discrepancy. Again, this has a very classic history. So again, if you just did a random coloring, it's not hard to see. You'll get a root n for the usual reasons. And already back in 1913, so more than 100 years ago, Steinitz shows that you can get order d discrepancy, where d is the dimension of these vectors. And the best known bound here sort of is root d root log n to Banaszczyk a few years ago. But so this is sort of an upper bound that we show, and the best known lower bound for this problem is root d. So there is still a gap here. So the third problem, again, it's sort of a famous problem in this area. It's called the Beck-Fiala problem, or the discrepancy of low degree set systems. So here you have a set system where each element lies in at most t sets. So think of t as sort of something much smaller than n. Or if you think of in the matrix view, the column sparsity of this matrix is less than t. Right? So each element is lying in less than t sets. But notice the sets themselves can be pretty large in cardinality, up to n. Right? So it's just the degree of the subsystem, but not the cardinality of sets. So again, if you did a random coloring, it could get up to root n. But a sort of famous result of Beck and Fiala from 81 shows you can get order t. And the best known sort of in this spirit is root t root log n, again due to Banaszczyk from about 20 years ago. And again, the big conjecture in this area is can you get root t? So we don't know any worse lower bounds. And this is referred to as the Beck-Fiala conjecture. And there is sort of a further generalization called the Combinatorial conjecture, which we'll see later in the talk. Okay, so these are sort of three classic problems which have received a lot of attention. Now, given such a problem, how do you show good bounds on discrepancy? So there have been sort of two aspects on this thing. So one is sort of the combinatorial bounds. So you just want to show like a combinatorial result that there is some good coloring that exists for a particular class of set systems, whatever. And sort of the second aspect is algorithmic, which is can you actually find such a coloring in polynomial time? Okay. So let's look at sort of the history, a bit of history here. So let's first look at the combinatorial part. So there was a long line of work, sort of pre-80s, based on sort of cute, elegant linear algebraic techniques, but sort of elementary techniques. And again, starting from the work of Steinitz back in early 1900s. So they get sort of basic results. A big breakthrough in this area happened sort of around early 80s and mid 80s by what's called the development of the partial coloring method. And this method sort of developed independently in the West and the East. So Beck and Spencer in the early 80s, sort of using a probabilistic method and pigeonhole principle, gave sort of a very elegant technique to show good bounds. And we'll see this later in the talk. On the same side, in sort of Russia, Gluskin gave a similar approach, very similar results, but based on sort of a convex geometric view, which we'll also see in this talk. And roughly in this partial coloring method, what you do is you're given some set system on these say elements. So you first find a partial coloring. So sorry, let's say of half the elements, right? So you color them and maybe get a good discrepancy for your sets. Then you sort of iterate this process log n times, right? Every time coloring half the elements. So you color the remaining elements and the other elements and so on. So this method sort of became the method of choice for lots and lots of discrepancy problems. It's very versatile. You can use it sort of in a very black box way and apply it very easily. One of the drawbacks of this method, however, is that since you do log n iterations to get the full coloring, right, like half elements get colored each time, sort of the loss can add up over these iterations, and you might lose a log n factor. But still, this is sort of a great method. And so this was sort of the second generation of results. And then in a major breakthrough, Banaszczyk developed another technique based on sort of much deeper convex geometric methods, where he sort of gave a way to produce a full coloring directly. So you don't sort of do what partial coloring does, where you apply this over log n phases, but you directly produce coloring, but sort of with slightly weaker bounds. And this it's a bit more non-trivial to apply, but you can also apply this in a black box way. So it's a very, very powerful tool, and sort of we'll see it in more detail later. So let's get sort of a sense of how these techniques sort of work. So let's look at the Tusnady problem, right, which was this coloring points in the rectangles to minimize the discrepancy with respect to rectangle. So if you look at this linear algebraic method, which was kind of ancient, if you apply it sort of in a non-trivial way, you get log to the 4. Then using partial coloring, again, there was a long line of work, but sort of it culminated in this work of Matuszek, which could get log to the 2.5. But then if you apply Banaszczyk's technique, which sort of produces this full coloring directly. So yeah, so this is this result of 2 weeks ago. So I mean, it took a while from Banaszczyk's result in '98 to Nikolov to sort of get this log to the 1.5. Yeah, so these sort of techniques get more and more powerful. Similarly, maybe if you look at the Beck-Fiala problem, again, linear algebraic methods kind of get you t. The partial coloring gets you root t times log n. Right? So you're releasing this log n because of this iteration over the phases. But Banaszczyk techniques sort of gets you root t times root log n. So this log n here became a root log n. So it's more powerful. But again, sort of there is a big gap, like sort of a gap here to close. Okay. Good. Okay, so this was sort of on the combinatorial front. Now, yeah. So one thing I should say, so these techniques, both sort of partial coloring method, it was, and also Gluskin's approach, they were both sort of very sort of based on probabilistic and pigeonhole techniques. So it was not clear how to make them constructive. And Banaszczyk was sort of even more maybe non-constructive, or at least if you sort of look at the proof, it wasn't clear how to make it constructive. So what happened in the last few years was, so we had a result about 7 years ago where we could show for many applications of partial coloring, we could make it constructive using sort of a random walk-based algorithm. And over the years, there have been sort of several new elegant and simple techniques developed for doing this. So in particular, there was a very nice algorithm by Lovett-Meka, which just used basic random walks and simple linear algebra to again sort of get the full version of partial coloring and make it algorithmic. So we'll see this later in the talk. And there was another very elegant work by Rothfuss, very simple two-state algorithm, which also got the same result. And besides these, there have been sort of more results in the last few years also, which sort of extend this in various ways and slightly different ways. Okay. So sort of the point is, all these partial coloring based results for these problems, they could be made algorithmic by any of these techniques. Right? So this was sort of in the last 5 years. But if you look at this part, based on Banaszczyk's result, there was still sort of not clear what to do. So yeah, so if you look at the algorithmic aspects for this Banaszczyk's thing, so one thing is we still don't know how to get anything for the general version of Banaszczyk. We don't know how to make it algorithmic. And there is sort of a nice alternate formulation of this problem by Dadush et al., which maybe I'll talk later if we have time. Right. So we don't know how to make it algorithmic. But what we could do is, there was a partial progress last year where together with Dadush and Garg, we could show how to make the Beck-Fiala result, give algorithm for the Beck-Fiala setting, where we could match Banaszczyk's bound of root t root log n. So this was a pretty tailor-made algorithm for Beck-Fiala setting. So yeah, so pictorially, we are sort of here in the bottom right. Right, so partial coloring methods only got you to root t times log n. But yeah, in this work, we could make Banaszczyk's result algorithmic. And more recently, yeah, we could sort of develop a more general framework. So we still can't make the general Banaszczyk algorithmic, but we can sort of give sort of a more general framework. So halfway maybe to general Banaszczyk. And the nice thing about this framework is you can sort of apply it in a black box manner without really knowing what's happening under the hood, sort of similar to like partial coloring method of Spencer, Beck, or Banaszczyk's technique. Right? So it's much more versatile. And as a by simple application of this black box, you can derive improvements for Beck-Fiala, Steinitz, Tusnady, all these very easily. So using this, in particular for Steinitz problem, we could again match Banaszczyk's bound of root d root log n. And similarly for Tusnady's case, so the best known using partial coloring was log to the 2.5. So using this framework, we could get it down to log square. And this was sort of, even before our work, nothing was known non-constructively to beat this log to the 2.5. But still, so now that we have this Nikolov's result of log to the 1.5, there is still a gap here. So we don't know how to quite close this. Right? Yeah, but this also sort of follow very simply from this framework. So this was sort of a rough history chronologically what happened. So here's the plan for the rest of the talk. So first I'll start with sort of giving you an overview of these combinatorial techniques, so the partial coloring method and Banaszczyk's result, a statement on how it's kind of applied. Then we'll sort of look at the Lovett-Meka algorithm based on random walks to make partial coloring things algorithmic. And so once we have sort of developed the basic framework, we'll see how this, say, the Beck-Fiala result, matching Banaszczyk bounds, follows by sort of enhancement of the Lovett-Meka technique. So in particular, we'll enhance their method using random walks, adding some extra sort of requirements. And then finally, I'll say maybe a few words about the general framework. Right? So most of the talk sort of will focus on this Beck-Fiala bound, Beck-Ferrara setting to match the Banaszczyk bound. So that's sort of the plan. So any questions at this point? Maybe. Okay, so if not, let's continue. Good. So let's look at the partial coloring method. So I'll give this view of Gluskin. So what Gluskin showed is sort of a very nice geometric result, that if you have any convex symmetric body, so symmetric about the origin, right? So if x is there, minus x is there, and suppose its Gaussian measure was, so this is an n-dimensional body, and suppose it's sort of 2 to the n to the minus n over 100. Okay? So again, these constants don't matter, but some of the point is that it's much bigger than, say, 2 to the minus n, which is sort of the volume of the cube, roughly. So sort of a substantially large body, but still exponentially small measure. Then the theorem was that any such body will have sort of a point in it, which has a lot of +1 or -1 coordinates. Right? So this point will be a -1, 0, 1 point, but lots of these guys will have non-zeros. So for example, in this picture, like a point like this here, right, will have this x coordinate like -1 and so on. So this body. Okay, and so this statement might remind many of you of like Minkowski's proof also for lattice point in a body of large volume, right? And indeed, like Gluskin's proof also is taking that idea and pushing it a bit further, but it's sort of a similar pigeonhole principle based on similar ideas. Okay. Right. So this result by itself maybe is not so useful in discrepancy. So a useful form happens when you think of this body K as like a polytope, whose constraints are given by, say, rows of a matrix, right? So here is a form that's sort of implicit in the work of Beck, Spencer, Gluskin, sort of that was maybe made more explicit by Lovett and Meka. So the statement is the following, and sort of it just follows like a direct corollary by applying this result. So the statement is the following: if you are given any m by n matrix A, right? So there is some partial coloring again of -1, 0, 1 points with sort of lot of +1s and -1. Let's say at least half of them are -1s and 1s, such that for each row, right? So this is just the discrepancy of row I. It's at most lambda I times the L2 norm of the row, and you can get any such. So you can pick any lambda i's you want, provided they satisfy this bound. And basically, the proof just goes by saying, if you just look at this convex body, defined by these constraints, its volume will be at least this much, right? So that's some simple calculation. We'll skip that. So let's look at this form. Good. So yeah. So let's actually see what this is saying in more detail. So I've written this statement here again. Now, one very interesting thing is it's sort of. So, we saw like for a lot of discrepancy problems, random coloring does not work. It gives a very bad bound like root n, but sort of there were these very refined bounds. And these refined bounds were just based on this statement right here. But if you look at this statement, it essentially looks like what Chernoff bounds tell us, but with a small difference. So let's do a thought experiment. Suppose we did a random +1, -1 coloring of this x, right? So x was a random +1, -1 vector. Then the probability that this constraint will be violated, so ai times x will be sort of bigger than lambda times the L2 norm of ai, should roughly be e to the minus lambda I square. Right? And again, sort of I'm ignoring exponents, the constants in the exponent and so on. But morally, it should be like this. So if you were just to apply the probabilistic method, it would say like some, or the union bound, it would say, right, the violation probability, if it's less than 1, then you will get such a coloring, right? Some constant probability and so on. Right. So if you just wanted to use probabilistic method, you could say, okay, if I had less than 1 here instead of n over 5, we could apply that. So what this is allowing us to say is, have a n over 5 instead of a 1. Okay, the Chernoff or probabilistic method. But sort of what we are losing is we get a partial coloring instead of a full coloring, like if you get a random coloring, right? So sort of that seems to be the only difference. And if you look at it this way, it seems, okay, so what's the big deal? I mean, we replaced 1 by n. But here is a very interesting thing. So notice, even if I make lambda I to be 0 for some set, right? then this term e to the minus lambda I square is just 1. Right? So in particular, what having this n over 5 allows me, I could take any n over 10 rows that I want and just demand that I get 0 discrepancy for them in my partial coloring. Right? So you would still satisfy this with some slack of n over 10 left. So yeah, we just do that. And sort of for the remaining rows, we can set lambda to be something like this. So this calculation still works out, right? So what's very powerful, having this sort of order n here instead of 1 allowed us to do this. Set demand even 0 discrepancy to almost a linear number of rows, which you could sort of never hope for in a probabilistic method. Right? And it's basically just this little or like this flexibility that we get that plays a major role in these discrepancy applications. So let's see what's happening. So let's look at a few examples to get a feel of this. So let's look at our Beck-Fiala setting. Right? So again, recall that in this setting we had sets with column sparsity t. Right? So each element sort of lies in only t sets, at most t sets. So how can we get sort of a root t times log n bound for Beck-Fiala? So the idea is quite simple. Right. So call a set big if it has more than, say, 10 times t elements. Right. So a priori, like sets can have any number of elements. But the point is, there can be at most n over 10 such big sets. And the reason is that if you look at this matrix, right, each column has at most t ones in it. Right. So the total number of ones in this matrix is at most n times t. And again, sort of one can show by a simple linear algebraic arguments that you can also assume that the number of sets is at least n. So n is at least n. Otherwise, sort of you have redundancy in your system and you can do better. So yeah, so you'll have at least as many sets as the number of columns. So just by an averaging argument, you also get that the average set size is at most t. Right. So So yeah, so if you have more than t times the average, then yeah, there can be at most n over t of that. Right? So just a simple averaging argument. Good. So if we have only such few big sets, by this previous partial coloring so flexibility, I can demand a partial coloring that gives a 0 discrepancy for these big sets. And sort of these other sets are small, right? So they have only fewer than 10 t elements. So let's say I demand a root t discrepancy for them. And it turns out if you set these numbers, you can still satisfy this equation here, right? So these are valid choice of lambdas. Right. So what the previous theorem will guarantee you is you'll actually get a partial coloring with just root t discrepancy. And then you do the usual thing of iterating this log n times and get a root t times log n. Right? So that's sort of the whole proof once you believe this partial coloring level. And as we see, like it was trivial to apply. So once we believe this statement, the application is usually quite trivial. Okay, so let's look at another example while we are at it. So let's look at the Tusnady setting. So again, here, so recall in this problem, we wanted the discrepancy of points with respect to these axis-aligned rectangles. So again, sort of by a simple, just a couple of lines of geometric argument, you can sort of define some canonical rectangles, just sort of a quadrita kind of a data structure, and show that if you have any axis-aligned rectangle, you can sort of write it as a combination of some disjoint canonical rectangles and some remaining log square endpoints. So again, I won't show this construction. It's sort of a very easy exercise. But yeah, so we have only a few canonical rectangles, and any rectangle can be written sort of as these guys plus some waste of log square endpoints. Okay. Now, once you have this construction, again, because I have only n over 10 canonical rectangles, I can just demand a partial coloring, which gives 0 discrepancy to these canonical rectangles. Right. So then what will happen? So actually, let's prove this Matuszek's result, right here, who showed this log n to the 2.5 bound, right? So if I look, so let's see. So we get a partial coloring, right, where these disjoint canonical rectangles have 0 discrepancy, so they don't add any discrepancy to my rectangle. Now I have these log square n points. So if I do sort of a random coloring, I can demand a square root of its discrepancy. So that gives me this 1 log n. right? So it's just the square root of this log square n. Now, maybe in principle, I could have n to the 4 such possible axis-aligned rectangles, maybe that I care for, right? So I will lose another sort of log mn, because I want sort of for each of these n to the 4 rectangles, I want a good bound. So I maybe use this in the union bound, right? Because for the non-canonical rectangles, you can sort of set this lambda. So this was the log n, square root of this, another about root log n by the Chernoff bound. And then we have log n phases, right? So like we get this much discrepancy, log to the 3/2 n per phase, and we repeat it for log n phases, and we get log to the 5 phases. So that's it. So again, sort of a very, very simple application once we believe the partial coloring statement.
Nikhil?
Yeah.
Can you say again where the what the m is?
Oh, m is the number of sets in the set system that you care about. So the number of rows in your.
But
right?
in this setting, what would it be? Are those just joint canonicals or?
No, so this would be all possible axis-aligned rectangle that you could have, right?
See, good.
Because those correspond to your sets that you care about.
And they would get log n extra, okay, because of the log squared endpoints. Okay, thanks.
Exactly. And again, sort of, we only care about n to the 4 rectangles, because any rectangle is sort of, combinatorially there are at most n to the 4 distinct rectangles you care about, right? Because for the top sides, each side.
Right.
Yeah.
And just to make sure, so these things are algorithmic because of your algorithm, right?
Exactly.
Okay.
So yeah. So once you make partial coloring algorithmic, all these things directly become algorithmic.
Okay.
Okay. So this is sort of how partial coloring was applied. It works beautifully. So let's look a bit more at Banaszczyk's theorem, which is the stronger hammer. So again, this is a very beautiful geometric statement, and it says the following. So suppose you are given some n vectors in some m-dimensional space. M could be anything, doesn't matter. And these vectors have, say, some constant Euclidean length, say 1/5. But again, these constants don't really matter. And now if you have any convex body with Gaussian volume of half, the statement is that there exists some +1 -1 signs, such that if you look at this sign combination of vectors, that lies in your convex body. So again, on the right, there is sort of a cartoon picture. So you have this big convex body with a large Gaussian volume half, and if sort of I pick some combination of these vectors, so this combination here would be right. Okay, so let's look at some, so this gives a lot of power. So let's start to sort of, see some corollaries of this. So if I choose my convex body to be the cube, but I need to scale its size by about.
Sorry, I have a question actually. How tight is this? Like, for example, if my Gaussian measure is substantially smaller, is there a counterexample to that?
So, okay, good question. Yeah, I don't know. My guess would be it should be tight for at least stated in this form.
Okay, I see.
Yeah, but we'll see, like, sort of for particular cases, like when k is this cube. I mean, so I'll describe this. This is a big open problem of Combinatorial. So I don't immediately recall the right example of. I'm not sure.
If you take a ball of radius square root n, then and you take n orthonormal vectors.
Okay. Yeah. Okay, good.
That's right, yeah?
Right, yeah, that should do it. Okay, good. Yeah, great. Okay, so I guess there are some bodies k for which it's tight, but yeah. So the question is, right. Good. So if you look at, right. So if you pick k to be the cube with sides about c root log n, again the Gaussian volume is at least a half, because if you pick a random point according to the Gaussian measure, right? No coordinate should exceed c root log n by some constant probability, right? So that's just that. And so what this immediately implies that if you give me sort of any n vectors of length at most 1, there exists some signs +1 -1, so that the sign combination has root log n length, or the L infinity norm root log n. So sort of this implies Beck-Fiala, the root t root log n bound on Beck-Fiala directly, because right. So if we scale sort of the matrix that we had by 1 over root t, right. So the column length now becomes just 1, the L2 length, because it had at most t once. Right? So the L2 goes root t. So if I scale by root t, it's at most 1, and then I just apply this previous theorem. So I get a root t times root log n discrepancy. And right, so this is coming to sort of this point. So in fact, we don't know for this particular body, when k is the scaled cube, whether root log n is the right scaling. So this is this famous Combinatorial conjecture, and in fact, it says, yeah, precisely for this problem that yeah, maybe the right scaling is constant. We don't know right exactly. So again, the point is, yeah, if you're given unit vectors, that could be +1 -1 signs. So that the L infinite term is at most order 1. This is the Combinatorial conjecture. Right? And again, if this was true, this would imply the root t for Beck-Fiala, which again we don't know. Good. So right. So again, you notice that of course the Banaszczyk's theorem is giving you the full coloring and not the partial coloring. So if you compare what we saw for partial coloring, so Banaszczyk is giving you full coloring as opposed to partial, but sort of, in a sense, it requires a stronger condition that this convex body have a Gaussian volume of half instead of in Gluskin we only needed sort of very small exponential, right? So there is a trade-off, but usually, yeah. So in most applications of Banaszczyk that I'm aware of, you only lose a root log n because of this requiring large Gaussian volume, and in partial coloring, you lose a log n because you do these log n iterations. Okay? So somehow Banaszczyk is sort of stronger, even though there is a priori no reason why it should be because of this condition. Okay, good. So this was sort of the basic history on the sort of non-constructive or combinatorial approaches. So yeah. So let's see how we go algorithmically beyond partial coloring approaches. So what our algorithm will do, as we said earlier, it will adapt this random walk-based method of these previous works, but sort of it will be good to understand what goes wrong if you try to do this directly, right? So sort of we'll try to enhance it, and it's good to see, yeah, the motivation for enhancing it in a certain way. So let's focus on what goes wrong. So again, let's look at sort of the Beck-Fiala setting as our canonical example. So what did we do there, right? So we said, okay, there are about n over 10 big sets of size bigger than 10t. So we could give them 0 discrepancy. And for these remaining sets, the small sets, let's just assume they were all size t roughly, just for simplicity. You could give them like a root t discrepancy, right? And then we did log n phases that gave us the root t times log n. So this is sort of what happened. But sort of this is a very pessimistic analysis, right? Like you're assuming that these errors in each phase add up in sort of an adversarial way for each small set. So what's maybe an ideal thing that you might expect, right? So let's look at the life cycle of a set. So let's look at so this sort of big thing is a set here. So let's say initially it was big, or maybe not, right? Yeah, right. So suppose it was big, then we, when we do a coloring of half the elements globally, you might expect that maybe half the elements of this guy also get colored. And since we have 0 discrepancy for big sets, you'll get exactly half reds and half blues for these elements you're coloring, and so this will not incur any discrepancy, right? And sort of this keeps happening until this guy's size becomes t, right? And then once you keep applying these phases, so now this set might incur like a root t discrepancy, right? So red and blue are not perfectly balanced here, but okay, you get a root t error. But still, you might expect that since you're coloring half the elements, like globally, maybe like this set should also roughly should get half its elements colored, and he should also shrink next time to t over 2, right? And now again, if you apply partial coloring, maybe the discrepancy you should get is square root of this size, right? The square root of t over 2, and then again it should shrink by some roughly half, and so on. So ideally, in the ideal world, if each set was also shrinking by half in every phase, just like the number of global elements was shrinking, you should expect a discrepancy something like this, right? Like a geometric series, which would be like order root t. And indeed, if this was true, like this would prove the Beck-Fiala conjecture, right? You would get a root t discrepancy. So yeah, so something should go wrong. Something is not as ideal as we would like. Right. So what could go wrong? And indeed, the trouble is, right. So yeah, when this set was big, we could demand it gets a zero discrepancy, so everything is nice and balanced. But then when it becomes small, all we know is this partial coloring will give it a root T discrepancy. But since it's adversarial, it could be nasty, right? So it could be like, okay, yeah, it got a discrepancy of root T, but maybe just root T elements got colored and they all got colored like blue, right? So the size of this set didn't really shrink, even though like globally you got half the elements. So some other sets maybe shrank much more, but this guy didn't shrink, right? And again, this could keep happening, and things, yeah. So this discrepancy could really add up in sort of an adversarial way. And the point is, this actually can really happen in sort of every algorithm we know. So it's not just sort of a theoretical bad case, but so let me, yeah. So it's interesting to look sort of at a particular algorithm and see how this can manifest itself. Right. So let me describe the Lovett-Meka algorithm sort of quickly in one slide, at least the main ideas, and then we'll see sort of what can go wrong with this algorithm and how we would need to enhance it. Right. So again, Lovett-Meka, what it's doing, it's making this partial coloring lemma of Gluskin algorithmic. So again, it was just this, right? So we want this discrepancy for each row I, this lambda I, and the L2 norm with this condition. So instead of n over 5, we have some different constant, but these things don't matter, right? So how does the Lovett-Meka algorithm work? You start with the all zero coloring, right? So let's call this x naught, and we'll proceed over time steps, right? So let xk denote the coloring vector that we have at time k. Right. So this algorithm starts with just sort of taking small random steps, right? So it's just doing a random walk in n dimensions. So in particular, in the beginning, you just update your color at time k, sort of each coordinate by, you look at the coloring at k minus 1 time and add a little Gaussian. So think of delta as sort of a very small number, like 1 over n or something. Right. So you're just doing a purely random walk. But sort of as this walk proceeds, if some variable reaches +1 or -1, you freeze it. So because you ultimately want to get a +1 or -1 coloring. So if somebody has reached +1 or -1, it's great, freeze it. Or what can happen is, as this walk goes along, maybe some row AI, its discrepancy gets tight, right? So you don't want it to exceed lambda, the L2 norm of AI. So if that happens, you just freeze it, right? So sort of this constraint here, that the discrepancy, or maybe more precisely, this constraint is maybe given by this hyperplane. So if you reach this hyperplane, then the walk sort of just continues in this hyperplane. It just moves in this subspace. And maybe it might hit another face, like a blue face or some other face of the cube and so on. So this game sort of keeps on going. So notice by design, you don't violate the discrepancy, because the moment you hit your desired bound, you sort of freeze. And sort of the idea of the analysis is that, because you have this condition here with this e to the minus lambda I squares, less than some Cn, sort of what you can show is that typically this walk will hit many more cube faces before it hits many of these constraints. And ultimately, when a walk hits like n different constraints, it will stop, right? Because there is, you have nowhere to go after that. So basically, that's the whole analysis. So like by the time you get stuck, you would have hit many more cube faces rather than the constraints. Okay.
Question?
Yeah.
Does this give a new proof of like Gluskin's theorem, or it uses it as a black box?
So it's exactly up to constants like here. Yeah, it's Gluskin's proof exactly.
Oh, okay.
I mean, yeah, constructive version of Gluskin's theorem. Yeah. Yeah. Good. Okay, so yeah, so again, I won't sort of give the analysis, but sort of that's the idea. But let's see what if we just do this. Some things can go very wrong. So yeah, so imagine we had some set of size t, right? Like say elements 1 through p. Now, yeah, so let's look at an ideal case, right? Like if we just randomly color these elements, right? We expect a discrepancy of about root t. And sort of the progress we are making is t because we are coloring all the elements, right? So this is sort of the ideal case to keep in mind. But in Lovett-Meka algorithm, what could happen is, so maybe if I go to this picture here, so every time you hit a constraint like this, you sort of only walk in this subspace, right? And it could happen once you sort of hit a few of these subspaces that maybe you are constrained to walk in this subspace that satisfies, like, the first coordinate should be the same as second, and so on up to the first t coordinates. Like maybe one constraint that became tight was x1 plus some other coordinates is 0, and x2 plus some same other coordinates is 0, and so on. So if these two constraints were hold, then this would force x1 and x2 to be the same, right? And since you don't have control on what are these other sets that are getting tight, it could happen that you land up in this subspace. But once this happens, something will go badly wrong, because if you're constrained to update your colors in this subspace, the only way you can do it is move in all +1 direction or sort of all in -1 direction, right? So to really make a progress of t, because you want to eventually color everything, you will have to incur a discrepancy of t, and that's not good, because you really want the root t, right? So in Lovett-Meka, I mean, these things can happen because there is no way to prevent it. So right. So of course, in that algorithm, you block a subspace if it reaches root t discrepancy, but then this kind of thing will imply that the progress that you make on such a constraint is only root t if you block its discrepancy at root t, right? So so this root t, exactly. So you're not making sort of enough progress. Eventually, you want to make a lot of progress because you want to color everything. But if you get correlated in this way, you will get a large discrepancy. Right. So I hope sort of it's clear what can go wrong by these correlations.
Nikhil?
Yeah.
Just to make sure, do you have an example, like an instance where Lovett-Meka doesn't give you the right answer, or just that some things seem like they go wrong in the analysis?
So you can create an example like this. I'm pretty sure. Yeah. Like this can happen all over the place. It's not a very rare event. But, right. I mean, you just need sort of these bad sets. Okay. Good. So the idea basically of this algorithm that we had initially for this Beck-Fiala setting was just to kind of prevent this. So the hope was, maybe we can avoid this by requiring your update steps to be a bit more careful or something, right? Right. So you could ask for this following extra property, and I have it here. So this is this key extra constraint, that when you do these update steps, right, at each step k, you update your coloring by some delta xi, you could demand, so this is like how much the discrepancy will get updated, right, at that step k for set S. So you could demand that the squared discrepancy is at no more like than some constant times the progress you are making for this set. So again, maybe it's instructive to look at this, right? So you are demanding to be in this setting, like the squared discrepancy here would be t. It should be bounded by the progress, upper bounded by the progress you're making, right? So this will not work because the square discrepancy update here is like t square, but this is only t, right? So you're sort of really forcing your updates to be independent in some sense and not correlated, right? So again, sort of, so think of these as delta xi as if they were +1 random vectors, then this would be about root s, and the square would be s, and here, if they were +1 -1, this would be s, size of s. So, but if they were all the same, this wouldn't be holding. Right. So in particular, right? So in this previous example, if these all got correlated for some reason, then sort of the only way to satisfy this, maybe except 1 or 2 coordinates, is to just set everything to 0. Right? Like the moment you make them correlated, in fact, if they are all equal, they must all be 0. That's the only way. So but the point is, right? So you got this subspace, this constraint, because these other subspaces that were getting tight, So because of that, you get sort of other dependencies that each of these individually must be 0 and so on. So it could be that this effect cascades and right, you get additional new dependencies and you can't get any non-zero update step. Right? So yeah, so the whole question is, okay, we can demand this thing, but why should it work? Like, why should such a step exist? And that's a non-trivial step. So what we would do is we'll write an SDP to get these update directions and sort of use a SDP duality to show that a good step exists. It's going to be the idea. And sort of we do it in the natural way. So yeah, maybe I don't want to go into too many details, but again, sort of the natural thing is to write an SDP for getting these update steps. So you define a vector variable vi at each time step k. So this should really be indexed by k, but I sort of don't want to create representation. So yeah, so these vi sort of give you the update, but these are vectors. So the way we'll get real values is just by projecting them on a random Gaussian, the usual stuff. Right. So you can write an SDP in the following way, right? So we wanted for big sets, you want a 0 discrepancy update. So that would just be this, right? So think of VIs as sort of delta xi at this point, right? So they shouldn't get any discrepancy. And this property of squared discrepancy change being the at most like the twice the progress, it just becomes this, right? So this is like the squared discrepancy update that we get is twice the progress that we are making. Now, for this big field, it just suffices to put sort of constraints like this and another similar set of constraints for a technical reason that maybe I won't get into here right now. But turns out that one can actually be much more aggressive. And in fact, you can put like an infinite set of constraints of this type, right? Like you can demand that for any vector b in Rn, yeah, so if you look at this combination of these vectors, it's at most this. So in particular, if these BIs were like the 0, 1 indicators of this set S, then it's exactly this constraint. But you can demand this sort of for every constraint. And the point is, yeah, like this complicated looking infinite set of constraints, you can just write it sort of as another SDP constraint on your gram matrix of V. Right. So it just sort of becomes a nice SDP, and yeah, you not only get sort of this property for your sets you desire, but sort of for every possible direction B. So I think it's sort of a very strong SDP. And turns out using duality, you can show it has sort of a non-trivial solution, a pretty good update step. Okay, so that's so again, I don't want to go in the proof of SDP duality. It's a bit technical, but not too much. Yeah, and we can show there's a solution. Now, one thing, so a very recent work by Levy, Ramdas, and Rothfuss, they show that you don't, in principle, really need the SDP view. Like, if somebody doesn't like SDPs, one can all do this argument also with multiplicative updates and sort of similar algebraic arguments that we use to show SDP duality. But at least, I think, yeah, maybe this SDP view seems a bit more clear and principled, like what's really going on. Okay, so yeah, so this idea of adding this stronger constraint of relating discrepancy to progress. There is one minor issue which I didn't completely address, or a kind of hand wave. So okay, so the reason we want to tie squared discrepancy to progress is that, you know, like once a set starts getting some discrepancy, we know its size has shrunk to at most 10t or whatever. Like if it's big, it doesn't incur any discrepancy. So if you could relate how much discrepancy you get to its sort of size, you're in business, right? Because if you look at the energy of a set, which is like just the sum of squares of its coordinate, we know that once it becomes small, this energy can rise by at most t. So if you relate your square discrepancy to the rise of energy, you'll always be within root t, right? So yeah, so you could define the energy of a set like this. But the thing I hand waved was, yeah, so the change in energy at each time step is this, right? So because this is the coloring at time k, right? The previous coloring plus the update squared minus what it was previously. So you kind of get this cross term and this quantity, right? But in this SDP constraint, we only related the square discrepancy to this guy. And in general, this guy can be arbitrarily large, because imagine your coloring was just fluctuating beyond a point, like around a point, like forever. Then every time you get a delta x, right? But its energy is not really rising because it's just fluctuating around a point. So we are still not done. But somehow the point is that the stronger constraints that we added, like these guys, actually make our life great. Because if you look at sort of this guy, right, by the strong constraints that we added, you should get, so each x k minus 1 is still between -1 and 1, right? It's the color at the previous step. So this whole vector is also bounded by sort of this, but this term is same as this. So the point is, yeah, so I cheated by not including this term, but sort of this term automatically disappears because it gets connected to this by these constraints that we added, and this happens for free. So yeah, so this is really sort of the whole proof in some sense. Yeah, I had waved a few things, but that's about it. Right. Yeah.
Yeah. So one quick question, just to summarize: do you understand correctly that the algorithm has the same high-level picture as the Lovett-Meka, namely that you perform this Brownian motion until you hit either a face of the cube or one of the constraints, and there you freeze. The only difference now is that you just don't just walk uniformly, not isotropically, but you can choose carefully what Brownian motion to do, like more towards certain directions.
Exactly. Absolutely. Okay. Yeah.
Okay.
Yeah. And these directions are coming from solving this SDP. Yeah. Good. So yeah, so basically, if you put these things together, yeah, you get a root T root log n for Beck-Fiala matching this Banaszczyk bounds, and this also extends sort of to the Komlov setting. So this was this previous paper with Bansal, Dadush, Garg, and sort of, yeah, so it's a nice result, but the drawback is, this algorithm and all its analysis was tailored just to the sort of Beck-Fiala setting, the proof that I described. And the analysis is also a bit complicated, and it's not clear, like if somebody wants to apply it for a different problem, how do you just do it in a black box way, like these previous sort of non-constructive approaches. So let me just say like one word about this general framework that we have. And the idea is you can use this framework to apply in a black box way, really without understanding sort of what happened in the previous proof. So if you're just a practitioner, you can use it directly. So the idea is similar to what happens in all these partial coloring or whatever examples that we saw. So the framework is sort of the set following. So again, we are doing sort of this update steps over time. But at each step of the algorithm, your algorithm can choose like n/10 sets that it wants to protect, right, or give discrepancy 0. This is also what was happening in this partial coloring. And then you apply this Gaussian random walk with this new enhanced SDP, and these sets protected. Okay. And the point is, right, so maybe here is a sort of cartoon picture on the right. So this green thing is this set whose discrepancy we care about. But you can protect certain red sets here, right? So in some sense, the only unprotected elements are these guys, right? And what you can show is, yeah, so call this element sort of corrupted if it was not protected at any time. Okay, so the informal theorem we can show is that, right? So the discrepancy of this set S that you'll get is kind of sub-Gaussian with variance at most the squared norm of these corrupted elements. And again, this is very similar to what was happening in this partial coloring approach, right? You could protect n/10 sets, but there you were losing log n because you were adding over each phases. But here there is no phase, right? It's just sort of a continuum. And you just look at the overall L2 norm of these corrupted elements. So in many cases, and this is sort of also what Banaszczyk buys you. So it gives you this full coloring. So the point is, yeah, like using this, we can recover all these different settings very easily, like half a paragraph every time. And yeah, so this general framework I think is sort of nice. Good. So just to conclude, so there are a few big open problems. I think sort of the most interesting question is for the general version of Banaszczyk's theorem about this convex body that we stated. We don't quite know how to make this algorithmic. So we can indirectly make these other applications algorithmic, but yeah, the general question is open. And maybe a first direction to attack this is to look at maybe more special cases, right? So for example, for Tusnady problem, we mentioned Nikolov has this log to the 1.5 2 weeks ago, and we could only get a log square. So maybe closing this would give some hints how to attack the general question. So of course, if you solve the general Banaszczyk, this would follow immediately, right? Because this is based on Banaszczyk. Similarly, there is another result called the L2 version of Steinitz problem. So we looked at the L infinity version, and there Banaszczyk actually showed a very nice root d plus root log n bound in a recent paper, but we can't match it using our general framework. So there is some sort of gap. And of course, sort of more generally, there are these big questions still left, right? Like for all these problems, there is still a gap, even non-constructively, between what's conjectured and or what's the best node bound we know versus what's, yeah, in Banaszczyk, the best results can. So that's it.
Thanks, Nikhil, for the talk. I guess if you have any questions, it's perfect time to ask them.
Yeah. Hello.
Yep.
I'm only familiar with the Beck-Fiala conjecture. The other two problems that you mentioned, I haven't heard before. I was wondering as to are there connections between them? That is, for example, if Beck-Fiala's conjecture is true, does it automatically follow that the others are true, or any such results are known connecting these three different problems?
Yeah, so I don't know of a formal direct connection, but indeed, like if you look at all these gaps, they're all root log n gaps, right? And maybe Steinitz kind of looks like Beck-Fiala, though not exactly, because Steinitz is about prefixes. So my guess would be if one could sort of solve Beck-Fiala, it should probably similar techniques should allow big progress on other problems.
But is there a formal result which says that if Beck-Fiala conjecture is true, then the Steinitz conjecture is also true?
So not to my knowledge.
Okay. Okay, thank you.
I have a question, actually. So you mentioned this Komlosh conjecture. Suppose for a second that I would like to disprove it, right? So for this, I need some bad set of vectors. So I have two questions, actually. First of all, did people try to find such systems of vectors that give constant lower bound, but like as high constant as possible? Are there any like partial results? Basically, this constant must be at least 3 or something like this. And second question, if so, how does this system of vectors look like?
Good. Yeah. So one thing is, yeah. So there is, I think, no consensus on whether Komlosh. Yeah, so like Asaf Naur, I think, believes maybe it's not true. But yeah, I'm not sure of any explicit examples. I mean, there might be like 2 or 3. I'm not sure, but nothing sort of substantially growing.
Okay, thanks. Okay, any more questions? All right.
Actually, just it's not really a question, but is there anything one can say about the general version of Banaszczyk? How far is your algorithm from solving it? It seems like you're really using the L infinity, but
Right. So good. So I have actually an extra slide on this, essentially. So it seems very close, but we tried it. So let me state this alternate reformulation of Dadushkar, Nikolov, and Lovett. So basically what our result for Beck-Fiala implies is the following. So again, let A be a matrix with unit length columns, unit vectors. Then what we are showing is indeed like there is some distribution on colorings, plus or minus on colorings. So that if you look at any row, its discrepancy is like O1 sub Gaussian, right? So that's why the max is root log n. So the Komlosh version of our result. So this is same as saying, if I look at any sort of row or EI. So EI is the unit ith vector. EI transpose AX is order 1 subgaussian. And what these guys show is that showing Banaszczyk is equivalent to showing the following. Like if you can find a distribution on +1, -1 colorings, such that if you look at any unit vector V, right, and look at this product, that's an order 1 subgaussian. So not just in this coordinate direction, but sort of in any L2 direction, and any L2 combination of these. So it seems very similar, but yeah, yeah.
This is distribution. This is something you can produce. You can sample from efficiently, right? That's the idea.
Exactly. Like for example, our algorithm is producing such a distribution. It is
sure. I see. But you really want to be truly sub-Gaussian in all directions, not just axis directions.
Exactly.
Okay. Thanks, Nikhil. Thanks the audience for making it to the talk. Before we conclude, let me just again mention that the next talk in 2 weeks will be by Jelani Nelson. Basically, he will show that very famous result, namely Johnson-Lindenstrauss theorem from 80s, is actually tight. This was open for a while, and finally this question is resolved. So we're very excited to have Jelani speak about it. Okay, I guess now Adet should put the talk off the air, and then we're pretty much done, right?
Yeah, but people are welcome to stay. Let me just take us offline.